Even the last time Lohit had joined and I forced him out of the meeting.
Yes,
Still that didn't work, and the recording still was owned by Lohit. So if a student
sir.
joins before me, then the video recording, even though the email comes to me, do you also get that email that this is the recording of the today's lecture or today's class from Google?
Which is
Yes,
asking
sir.
for permission, sir.
Yes, sir. Some permission. I mean, some emails came to me regarding the permission, so I gave them
Okay,
the.
you give the students the permission.
Yeah.
Okay,
So this
yeah.
time
So
I joined late, so that this problem
yes,
won't occur.
yes. So yeah, so if any student joins before me, then the file will go to them, and then everybody else will not have the permission. If file comes to me and I'm sharing it, then automatically as soon as I share it, everybody would have the permission. And also I want to keep a video file for my record also, but I can't do that if you own the file. Then I'll also have to take permission from you to give me the ownership, and I don't know whether it can be even done or not. So yeah, so today I tried to join much earlier than others, so that hopefully I'll be able to do it. These are some glitches with Google. It does not differentiate between the teacher and the students. You're all equal in Google Meet. Okay, so I hope they will be improving these functionalities soon. Anyway, so the recording has started already. Fine. So tension members are the most or the simplest kind of structural members that you can come across. So where are in structural systems tension members used? That is the first question that you may have to think about. So can somebody give me some examples of where do you get to see tension members used frequently in structures?
Trusses.
In trusses, yes. What kind of trusses? Can you give me an example of a truss? Yeah. No?
Roof trusses, bridge trusses.
Okay, so in a bridge truss, can you tell me which members would be? So
Bottom, mostly bottom members.
mostly bottom. Yes. So if you have a plain truss, let's say somewhat like this. Okay. This is a typical truss, a bridge truss maybe, or a roof truss also. A roof truss is often shaped like this. Correct? So no matter what kind of truss it is, typically trusses that are designed to carry the gravity loads, the bottom chord, yeah, that is almost always under gravity loads, almost always in tension. These members will be in compression. Similarly, these members will be in tension. And then what happens is that some of these members will also be in tension and compression alternatively, or something like that. Some arrangement would be there. Yeah. So these are all diagonal members or vertical members. Vertical members will mostly be in compression, but diagonal members may be in tension. Okay. So bottom chord in a roof truss, that is most often in tension. Now, also when you have towers, bridges, etc., under, let's say you have a tower structure, which is also a truss. You may have a triangular tower also, right? Triangular base. This is the other leg. So which company makes triangular base towers? Anybody knows? I'm talking about telecom towers. In India, nobody knows.
No, sir.
Do we have any which telecom operators have a decent signal on our campus? IT campus. I mean, of course, first year students won't know.
BSNL.
BSNL signal is good because BSNL has got the direct access to our campus. They have put an antenna inside the campus. Which else?
Airtel.
Airtel. Where is their antenna?
Maybe besides girls hostel.
No, that's not Airtel. Have you guys investigated that, trying to figure out which signal, which mobile company that is, where the signal is so good?
No, sir. I'm just
Yeah,
guessing.
that is Geo.
Okay.
GIO, right? I don't know how to spell it. Yeah. So actually, I mean, I have worked on some telecom projects. That's why I know. This is not something you have to know as a structural engineer. Geo tends to use these triangular base towers, which are tubes. So the main legs are all tubes, and these are all angles. Okay. So they have this kind of a gusset plates, and on these tubes, and these tubes may have sometimes splicing, and splicing is tubular splicing is of very different kind. Splicing basically means when the tube section is tube length that is available to you is not long enough as the full member size, then you have to do the splicing, and this splicing is done through an end plate, okay, circular end plates, which are welded to the member and bolted together. And then you have these angles which are bolted to the gusset plate, and the gusset plate is welded to the main legs. So when there are wind loads, etc., acting on this tower, then some of these braces will undergo tension. Okay, so the braces are primarily the other types of members which undergo. So bracing systems, it could be in a transmission tower or telecom tower, or it could be bracing systems in a building. So buildings also have bracing systems, right? So if you see any tall building, if you remember my first lecture, we were talking about these tall building structures, and most of the steel tall buildings have this bracing system. Okay, mostly you will see X bracing very often. So this is called X bracing. So when the lateral load, when any kind of lateral load acts on this building, so let's say this kind of lateral load is acting on this building, then you would have this brace undergoing what kind of forces? This particular brace.
Axle forces.
Tension?
Axle forces.
Action or
Compression.
compression or tension?
Compression.
Compression, right. So this will be undergoing compression and this will be undergoing tension. So in each story, you will have one set of members that are oriented this way. If the forces are acting this way, will be in tension, and these members will be in compression. Okay. So braces are the other types of members which can be subjected to significant tension. Then you may have cables and pre-stressing strands, etc. But those are not the topic of the interest as far as structural steel is concerned. So we are talking about members, designing of members which are not in that domain. Okay, so we are not talking about cables, etc. Okay, so the things that we are talking about in this course are angles, plates, flats, not even rods, and then maybe I sections, etc., and T sections in double angles that are designed in tension. Okay, the other things, not rods so much, and rods can be okay, but tubes we will not really pay much attention to, and strand or ropes we are definitely not talking about. Okay, these are the different sections that can be used in tension, but we will be limiting our discussions to only these members that are underlined. Okay, so whatever we are discussing may not be directly applied to rods, ropes, tubes. Okay, so basically, design of any member has two considerations. One is the strength consideration, and the other one is serviceability consideration, right? So for tension and compression members, generally serviceability considerations are not that significant. Serviceability does play a role when we are talking about overall deflection of the building or a tower or the bridge, but that is limited to that extent. So overall deformation of the structure, and as a result, individual deformation of individual members is not that significant, and that's where the serviceability limits are generally satisfied. So for members in tension, serviceability limits generally do not have a very significant effect. There are some limits on the overall slenderness of the member, and I think I have a slide at the end for that. Yeah, this slide. So we'll talk about it. So as long as you meet those slenderness limits, you are generally okay. Okay. So then the other consideration for designing any structural system or structural member is the strength limit state. Okay. Can somebody, I have not explained this so far, but can somebody tell me quickly what do they understand by strength limit state and serviceability limit state? Since you have taken this course as an undergraduate, you should have some understanding of this thing.
Strength limit.
Lohit, maybe somebody else can be given a chance. I know that you might probably know the answer, but let somebody else try.
So strength
Strength
mainly
criteria considers only the resistance values, sir.
Okay, Harish, let Leo try once. Sorry.
so
The strength criteria.
Harish, can you please wait for a minute? Leo, please go ahead.
so strength criteria means mainly depending on the material characteristics of the material. When steel, like in serviceability criteria, we are mainly dealing with the deflections, cracks, like that. That criteria is maintaining.
Yeah. So strength criteria, like strength limit state. Do you want to try again?
Strength limit state means we are mainly reducing the strength parameters. Means strength, reducing the strength, underestimating the strength, and for designing purpose, and overestimating the loads, like that.
Okay. Okay. Yeah, Harish. Now you want to give it a try?
Sir, yeah, the strength criteria, it basically checks for the resistance values, sir, for the
Yeah.
applications. Whereas the serviceability, it checks for the service life, sir, not the resistance particularly.
Service life. Be careful with what words you are using. It's not
Like
necessarily service life.
we check mainly for deflections, sir.
Correct. Yeah. Anybody else wants to give it a try?
Sir, strength mainly refers to the stability against overturning, and in serviceability, it mainly refers to the vibration.
Vibration deflections. Yeah.
Yes, sir.
Okay. So overturning is a good point, but it is not just that. Correct. Yeah. All right. So I think, see, all of you, if I just combine whatever you were saying and maybe a couple of extra words that you had used, I may have to remove those. Other than that, I think generally the understanding is fine. Okay. So you can think of it as this. So if, for example, strength limit state exceeds, so I design a structure and I apply the loads, and somehow the loads, I made a mistake in designing or whatever, or loads exceeded, whatever. And the strength limit state exceeded and the structure failed the strength limit criteria. Okay. And when it fails, it will have some kind of a damage. And as a result, the structure will not be usable. Okay. It will not go back to its original state. Fine. However, in the service limit state, if that is exceeded, and I'm not saying exceeded by 100 times, exceeded beyond what is mentioned, okay, the structure will still be, once you remove the loads, the structure will be perfectly usable. Okay, only at that time it will not be able to serve your requirement of the service conditions, right? So your service limit states are the kind which are only causing you some kind of a discomfort, or your functionality is not satisfied. So you want a floor to be flat. You don't want the floor to have a slope, or a slope large enough so that your chairs start to slide. Like if your chairs have rolling wheels, then the chair should not start to move on automatically on the floor, just because the floor has so much of slope. And likewise, so, but as soon as you remove the loads, the floor will go back to its horizontal position, and then the structure is usable. Okay. Such kind of situations, such kind of conditions are put into serviceability. Okay. So they are not endangering the structural integrity of this system. Okay. They are not endangering anybody's life. They are not endangering the stability. Okay. Because if there is a stability issue, so all these words that Shayan has said, stability. Yeah. So stability comes under strength. Okay. Now, so serviceability could be this, serviceability could be vibrations. Yes, so as people are walking in the next room, I should not get disturbed by their walking. Or if a vacuum cleaner is operating in the next room, I should not get disturbed by that vibration of the vacuum cleaner. Right. So all these things will come into within the ambit of serviceability. The strength limit states will be the ones which, if exceeded, then I will not be able to use that building again, because the building will have a significant permanent effect. Okay. Or the structure, not just the building, any structure. So basically these kind of limit states could have many various types of, at the material level or at the member level, you may have various aspects or various manifestations of that kind of limit state. It could be yielding of the metal. And then when we say yielding, we don't always restrict yielding. So there would be a limit to the yielding that we allow. Yielding, it could be rupture, it could be buckling, those kind of things, bearing failure, shearing rupture, shearing deformations. We can give different names, but if you look at the material level, it is mostly either yielding or rupture, or at the member level, it is mostly buckling. Okay, or at the system level, it could be buckling. So these are the 2-3 primary types of limits that govern the safety of the structure. The second one, the strength limit state, is generally something to do with the safety of the structure. The first one is not so much to do with the safety, but more of the comfort. Serviceability limit state is more on the comfort side of it, and this is more on the safety side of it. Okay. So as I had mentioned, the 3 types of failures, or the strength limit state, may have 2-3 different manifestations as far as material is concerned, and 2 important ones are yielding and rupture. Okay. So the limit states that are typically considered when we design a member for tension, one is yielding of the overall section. If you have a bar or if you have a plate which is in tension, then it has to be designed as if for the overall cross section against yielding. Okay. And also sometimes what may happen is that the cross section may be reduced at some locations. You may have holes in the cross section, and if that is the case, then you have to worry about the net section. And in those conditions, when there is a net section present which is smaller than the overall section, then you don't worry too much about the yielding of the net section. You only worry about the rupture of the net section. In addition to that, there are some limit states which are basically a combination of yielding and rupture, which is known as block shear. And then there may be bearing stress, but bearing stress failure we will talk about when we talk about connections. We will not discuss them in the tension members, because that happens only when you have a bolt or a rivet sitting inside the hole. Okay. And then there is something called shear lag effect that is often joined with the net cross-section area availability. And then the 2 together play a role, and that we will talk about a little bit in this chapter. So these are the primary topics to talk about. Okay. So we will start with the first 2, the yielding of the overall section, and when you have a reduction in the cross-section due to bolt holes, then we talk about net area rupture. Okay. And we don't worry about the net area yielding. Fine. Do you understand the difference between net area and gross area or overall section? So for example, if I have a plate like this and it is extending, this is the longitudinal axis of the plate, and that is the axis in which the forces are acting. Okay. And there is a hole in this plate, and the purpose of the hole could be to use it as a connecting place. So you can put a bolt through this hole to connect this plate with another plate. Okay. And this plate is subjected to tension. Now, this tension could be acting because of the presence of this bolt, or it may, this hole just may be there and the tension is coming from somewhere. It doesn't matter. So in this particular case, what is happening is that you have got this plate, you are applying tension force, and there is a hole sitting right in the middle of this plate. So away from the hole, you have a gross cross section available, and right at this hole, if you draw a line across this plate, across the width of this plate, you will see that there is a reduction in the cross section. This portion of the cross section is not participating. Okay. Now, as a result of this reduction in the cross section, theoretically, if I didn't have good understanding of the material behavior, I would have said, okay, total area was AG, but the reduced area would be A net, which is by excluding the area of the hole. So A net multiplied by Fy would be the strength limit state. Okay, right? A net so if I have plate, this B is BG, or I can just call it okay. So in this plate, if I take a cross section here, that cross section will be called AG, gross cross section. But if I take that cross section here, then this cross section, which is excluding the area of the hole, will be called A net. You follow?
Yes, sir.
Okay, so I would have said that AG multiplied by Fy would be the limit state if there are no holes in this plate. But if this plate has any hole anywhere along the length, then the available strength will be only A net multiplied by Fy. Okay, but that's not what the code says. The code says we need to do Ag multiplied by Fy. Okay, that is one limit state, and the other limit state is An multiplied by, what is the value here?
FU.
Fu. Okay, and then just to be on the safer side, let's put a 0.9 here and also use a different gamma m1, a different gamma than here. Okay, so the code says don't take this one, A and Fy. Don't take this. Can somebody tell me why does the code say that you don't have to worry about yielding around this hole? Yielding of the net cross section, you don't worry. You only worry about rupture of the net cross section and yielding of the overall cross section. So either this cross section can yield or this cross section can undergo rupture ultimate. Can somebody tell me why do we not worry about yielding of this net cross section? Otherwise, I would have had this one divided by gamma m0 also. The clues are
yielding-
yeah, go ahead. Who is this?
So,
Yeah, Leo.
for yielding, it required more load, where in a rupture, it's required only less load. So, it will be the minimum worst section for rupture, like failure condition. Like,
No, Leo, I was not sure what you meant. See, if you, that 0.9 is a made up factor, right? So let's not consider 0.9, and gamma m1 also we can talk about where gamma m1 comes from. So let's not put the factors, include the factors in the discussion. So if we remove the factors from the discussion, then you have one limit state, which is yielding of the net section. That says An multiplied by Fy. And this is the other limit state, which is rupture of the net section, which is An into Fu. Now, Fy is, let's say, 250 MPa. And Fu is 410 MPa. So how can we say that this is higher? This is lower, right? A and Fu, A and Fy. So why aren't we consider A and Fy, and why are we considering something bigger? Right? This is typical. These are the typical values, right, for your 410 steel. Yeah, somebody else wanted to try? Or Leo?
Sir?
Yeah, Asadullah.
Sir, in net area, the length of the plate is very less, sir. So the
Yeah.
deflections also less we can allow up to your net ultimate stress, sir. in gross area the length is more, that's why we can allow up to yielding, sir. That's why we take Fi in gross area.
In gross area, length is more. That's why we allow only up to
Fi, sir.
yielding.
Otherwise deflection will be more. We allow
Reflections
up to
will
net.
be. Yeah. Yeah, that's the almost the correct answer. Did anybody else follow? Like other guys follow what he was saying? Okay. So basically, what happens here is that if you look at this section again, I'll just erase some of this. It would have been easier for me to draw it again. So if I take that plate again and I'm drawing only 2D. So what happens here is that the way steel behaves, I'm drawing the stress strain plot of steel. In true scale, this is how the plot will look, right? So this scale is the strains here from here to here are much larger than the strains from here to here. Now, let's say there is also a hole in this plate. Okay. And it is subjected to a tension force. Now, let's say this section starts to yield somewhere here. Let's say as we increase applying the force T, this section will start to yield first, right? Before this section picks up. So let me call it section N and section G. Correct? So section N will yield before section G yields. Everybody agrees with that?
Yes, sir.
Yes, sir.
Because average stress in section N will be smaller. Sorry, average area is smaller. So average stress in section A is larger. Okay. So now what will happen is that there should be some yielding here. But if there is going to be any yielding, that will typically be distributed only in this width. So this portion of the cross section of the length, this much length of the member will be yielding. Okay. And let's say before it reaches the rupture point, it has a maximum deformation of 20%. Okay. That's what we allow. Or actually 20% is there. Sigma U, we are restricting, right? So it will be something approximately, let's say 15%. That is the strain value. So the length change in the member will be approximately 15% of this length. Okay, that is the whole diameter. And even of the whole diameter, the entire length will not be yielding. Only where you have the smallest cross section, only that portion will be yielding first. Okay, so then you are going to get to 15%. However, here, if let's say the yielding starts, then there is no restriction that the yielding should be limited to only here. Yielding can spread here, yielding can happen here, can happen anywhere. And in fact, once this yielding happens, this section will start moving on this path and the stresses will climb up slightly. So as soon as the stresses start to strain harden here, the yielding will happen here also. Okay, there is no special preference why this yielding should happen only here and not here and not here and not here. And that yielding can actually take place over the entire length of the member. Correct? And of course, after some point, there will be some necking and so on, and those things will make the yielding more concentrated. But still, if you imagine the amount of length change that you will get as a result of yielding here will be, if let's say yielding is at least distributed over the width of the member. Okay, so the width of the member is, let's say, B. Okay, so you can very easily assume that the yielding will be distributed over a length that is equal to B. If the width is B, the yielding can very easily be distributed over this length. Okay, if you have done a coupon test, you know that, you must have seen this. So this much of the area will definitely yield if we are talking about gross yielding. Okay, so we don't want to exceed this limit, because once we exceed this limit and we push beyond the yielding, then this point will not yield, but the other point will start yielding, and the subsequent point will start yielding. The entire member will yield. Okay, or even if the other parts don't yield and there is a necking forming here, still you are going to have a very long length. So then you will have 15% of your B value, that much of elongation. Whereas in this case, you have only 15% of your whole diameter, and not even that much smaller than that. That is one argument. So overall member length deformation under this yielding of the net section is very small, but overall length deformation under gross yielding is very large. So we restrict gross yielding. So gross yielding is restricted. So therefore it works as a limit state, but yielding of the net section is not restricted. So we don't mind if the net section yields, therefore it is not restricted. We go beyond it and we go up to FU for this section. We are willing to go up to 15%, but we don't want to go to 15% of the gross cross section. Okay, that makes sense. Also, other argument is that anyway, when we have a plate with some kind of a geometric irregularity, holes could be one type of geometric irregularity, and the plate is under uniform tension. So tension stresses away from the hole are all uniform. But what happens when we come closer to the hole, to this geometric nonlinear geometric irregularity? What happens in this cross section? How are the stresses distributed? Okay, if you look at this one, the stress, there is something called stress concentration under elastic state. Okay, so under this kind of state, what happens is that if away from the hole the stresses are same as this, almost same as this, of course you have to deduct for the area that is not available because of the hole. Right next to the perimeter of the hole, at this point, so if this is the hole, right here in this area, and right here in this area, you're likely to have the highest stresses. Okay, and that comes purely, it can be in fact analytically it has been derived how much that value should be. So if everywhere else the stresses are this much, right here the stresses will be almost 3 times higher under elastic conditions. Okay, okay, and this will be in tension. Is that clear? So because of that, what happens is that even when we are targeting, let's say, a value of Fy here, the value here will be almost how much? 3 times Fy. In other words, we cannot avoid yielding in the neighborhood of the hole. Or if, in other words, what we can say is that if we target this value to be Fy, if we don't want any yielding, then elsewhere the value will be Fy by 3. That is very, very low utilization of the material. Just because there is a hole present in the plate, the stresses here will be restricted to only Fy by 3 if you want to prevent all kinds of yielding. Okay. Otherwise, you allow it to yield, then the stresses, if you go to plastic state, then the stresses will everywhere will be Fy, because beyond Fy anyway they can't exceed. So the stresses will be Fy everywhere. Okay, and even if it reaches Fy, all you have is only about 15% of that deformation. The deformation, longitudinal deformation that you cause, or the portion of the member that is permanently deformed, is only this much. This much length of the member is deformed. Okay, and considering all this, we tolerate, we don't mind the yielding of the net section, and we go beyond yielding and we go up to rupture point, and we design for that. Okay, so either we consider yielding of the overall section, and we consider rupture of the net section. Okay, and considering all this, we take whichever is the lower, whichever gives us the lowest capacity, because we don't want the cross-section, overall cross-section to yield, and also we don't want the net section to rupture. The rest of it we allow. Okay. Then you have a block shear. We will talk about block shear failure. I'm sure you must have all studied that. Block shear is basically a combination of tension and shear. It arises in certain conditions. When we talk about the net area calculation, then block shear will make more sense. And then there is bearing stress. We will not talk about. This point is more suitable for connection design. Then we can talk about the shear lag effect. Okay, so basically the design strength of the member in tension, TD, is equal to minimum of TDG, comma TDN. Okay, the design total strength is equal to minimum of the two. One is gross yielding. Let me see if my IS 800 we can find that line. Okay, so here you should design the member in such a way so that the force acting on the member, that is factored force or tension demand, is less than the tension capacity, design tension capacity, ED. And tension capacity, you can see this screen, right? IS 800.
Yes, sir.
Yeah. And design tension capacity is the lowest of the design strength due to yielding of cross section and rupture strength and block shear strength. So I should rather say okay. So this is the cross section yielding. This is net section rupture. And this is block shear. Okay. So the minimum of the three, that is the total design capacity. Okay. And you know each one of them. So TDG here, that is A gross Fy by gamma M0. That's what I have mentioned here in the top. Fy Ag divided by gamma M0. 1 second. Okay. So cross section multiplied by the yield strength divided by gamma M0. What does gamma M0 stand for?
Partial safety factor.
Partial safety factor for resistance. Yeah, but it is applicable. Gamma M0 is applicable for limit states of yielding and buckling only. Agreed? Let's look for gamma M0 in table 5. So here is table 5, page number 30 in IS 800, where it gives you the gamma M0 values. So if you look at this one, resistance factor, gamma M0, governing yielding, and similarly governing buckling. Both of them are gamma M0, and the values are 1.10 in both cases. Okay. Fine. So yielding of the cross section is straightforward. We don't consider the yielding of the net section. When we say we don't consider, what does it mean? Does it mean that we don't allow the yielding of the net section? Okay, I'm going to ask by the name. Vishal?
Yes, sir.
So we consider one limit state was yielding of the gross section. The other
Yes,
one
sir.
was rupture of the net section. But
Yes,
we
sir.
did not have yielding of the net section. So
Yes,
basically,
sir.
so do we not allow yielding of the net section?
No, sir, it's not like that. It's like the net section won't fail by yielding, but will fail by rupture.
It won't fail by yielding. That's the kind of a confusing sentence to me. It will not. Can you try to reword it? Not fail by yielding means what?
Means the governing situation in net section will be rupture, not yielding.
What happens at yielding?
Uh, so I mean,
Does it not yield? Like it will not yield at all?
uh,
Before it goes to rupture, it will have to go via yielding, right? Because the stress strain plot for steel
sir.
is such that
Sir.
before you go to rupture point, you have to go through yielding. You cannot jump from zero stress all the way to yielding or all the way to rupture. So you have to go past yielding, right?
Yes, sir.
Yeah. Shayan, you want to give it a try?
Sir,
Hmm?
no idea, sir.
Haripriya? Yeah, you want to make a guess? What is happening with the yielding of the net section?
So I'm not sure about that.
But I spent almost like 15 minutes explaining that, so that is not a good enough response. I'm not sure about it. Come on, you guys, you have to listen more intently, otherwise you have to ask questions at least. Kelvin, you want to try?
Yes, sir. So the strength will be the yielding capacity of the net section will be less than the actual yielding capacity of the go section. So if you use the net section yielding capacity, you underutilize the strength the strength of the entire section basically.
So you're saying that yielding capacity of the net section will be lower than the yielding capacity of the gross section, which is true. But why? Then how do we ignore it? Why do we ignore it? Do we ignore it, or does it not even happen?
Sir,
Kelvin, you want to try again, or you want to pass?
That's all. Let's try. Let me think, and then I can try to come back later.
Okay, Asadullah, you want to say something?
sir, of course it yields before rupture, but it does not have much more effect on the structure failure, sir. That's why we can.
That's why what do we do?
That's why we can allow up to rupture, sir, net section.
Correct. Yeah. So see, the thing is that Lohit.
Yes, sir. Anyway, we can't avoid that. I mean, near the at the net section. Anyway, we can't avoid the yielding. But even if you avoid the yielding, the other material, the material which is far from the hole, it will be underutilized. So we won't mind whether whether it is yielding either. The only concern is it should not fail in rupture.
Yes. Yeah. So again, listen to my words very carefully, people. This is important. That's why I have spent so much time here. See, what we are saying is that, so this is where the hole is, and away from the hole, we don't want it to yield. But right at the hole or in the cross section that passes through the hole, we cannot avoid that cross section yielding. If we do that, if we don't want any yielding to happen here, then the stresses everywhere will be very low. Okay, that is very, very uneconomical way to design. So we allow it to yield. When we allow it to yield, the entire cross section goes to yield point, but then still the member has not really failed. Okay, and failure is of course within inverted commas, because it is up to us to define what failure means. What happens is that member becomes flexible for a while. and over that small length, it becomes very easily deformable. Okay, and that over length expands a little bit. Okay, but over a very small length, it can expand easily, and that expansion does not overall change, is not very significant, and overall the member does not become very flexible, right? So the additional deformation that we are getting because of the yielding in that neighborhood does not significantly alter the member stiffness. Okay, for that reason, we allow the net section to yield, and we don't consider that as a limit state, or we don't mind the net section to yield, but we don't want the cross section to yield, so that is a limit state. We don't want the net section to rupture, so that is a limit state, and there are formulae given for that. But we don't mind, or in other words, we allow the net section to yield, and therefore there is no formula given for that. Okay, so let the net section yield. That is the philosophy. Okay, I hope it's clearer now.
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, good. So yeah, I mean, I may come back to this thing again sometime later, and I want to have a better response from you people. Okay, fine. So all this discussion that we are doing here is with respect to a section that is uniformly loaded, and it need not be a plate. So the examples I showed you here was for a plate, but it may also be an angle. Okay, so it may be applicable to an angle also, as long as we make sure that the entire cross section is loaded uniformly. Okay, it may be applied to an I section also, but again, as long as we make sure that the entire cross section is loaded uniformly. Is that easy to ensure? It is very, very hard to make sure of such a thing for I sections, for angle sections, but it is much easier to do that for a plate or a rod, okay, or even a pipe. So therefore, these equations are applicable only when the stresses are uniform. That is, we are applying the stress which is, or the net force is acting at the centroid, and it is applied far away from this location of interest so that it has distributed uniformly. Okay. Now there comes the question of net cross section. So if you have a plate with a single hole like this, then what is the net cross section? This is total B. The diameter of the hole is D. So my net cross section and the thickness is T. Thickness of the plate is, drawing two parallel lines is very, very hard. Okay, thickness of the plate is T. Then the gross cross section area will be how much?
B minus D into T.
Gross.
Of B into T.
Yes. And A net will be
B
minus T into T multiplied by T. Okay, simple, straightforward. There is no challenge. What happens next is, sometimes we may not have a single hole, we may have more than one hole, and the two holes may not always be aligned in the direction of the load. So if we have two holes and the load is acting in this direction, then the two holes are aligned in such a way so that they pass through the same perpendicular line that is in the direction perpendicular to the load. Then of course it will be B minus 2D times T, correct? However, you may also have a situation where the holes are staggered, which is not a very uncommon situation. Okay, why do you have to do that? To sometimes you have to do this to put as many bolts as possible in the smallest possible length. Correct? So if you make it a square section, like a square pattern, then you may not be able to put as many bolts. So if you want to densely pack a large number of bolts within this shorter length, sometimes you may have to go for this kind of a staggered arrangement. When you do that, basically what happens now is that the fracture path, because we are talking about net section rupture, that rupture path may pass like this through the holes, okay, or the rupture path may pass like this through the holes, or it may pass like this. So one, I'll call it 1, or I can call it 2. Or I may have 3. Okay. Okay, so likewise, you can have various paths possible, and then you need to consider all such possibilities. Now, in these paths, what's happening is that your fracture path is not really passing exactly perpendicular to the load axis, right? So the stress state right before rupture is not pure tension. So you are not exactly in the pure uniaxial tension domain. If you look at this portion, so the rupture path may be inclined with respect to the load path, right? They are not exactly perpendicular. So you are not under pure uniaxial tension condition. It is some shear, some tension combined. You understand that, right? If this is the rupture path, then there will be some shear stress also on this axis. Fine. So in that case, what is the capacity? So either you can go on the first principles and try to derive the von Mises stress and try to see at what point the rupture will take place. But in 1920s, some empirical equations were developed, and instead of actually following the first principles, they came, or the failure theories. These are not, the failure theories themselves are not first principles, are not derived from first principles. But if you these expressions are available, which were developed in the 1920s, and even American code uses the same equations, which allows you to calculate the net cross section for a given rupture path. Okay. So you can consider all such possible paths. You can consider 1, you can consider 2, you can consider 3, and do the calculation and see whichever one gives you the smallest AN value. Okay. Right. And where in this expression you see that B minus NDH. So B is the total width minus number of holes through which the path is passing times the diameter of these holes. That was straightforward. Plus, then you have to do some addition because these paths are not perfectly perpendicular to the load axis. In such cases, for them, you have to do some additional area, and which is equal to sigma, that is summation of all P square by 4Gs. P is the pitch. So for one path, let's say one portion of this path, let's say this path, you will do this P square divided by 4 times this distance. Okay. Likewise, you keep calculating, and for all the paths, and then you see which AN. So you will get AN1, AN2, AN3, depending on various paths that you're considering, and then you compare them. Okay. If it is a rod and if it is not threaded anywhere, then you will take the AG yielding only. But if it is threaded, rod is also often used as a tension member, especially as a brace. The rods are often used. Has anybody seen a rod being used as a brace at IIT Hyderabad? Again, first year students may not know. Have you seen a rod being used?
Maybe at the 7th floor.
7th floor.
Maybe.
Yeah, there are some heavy. Yeah, there are some heavy rods on the 7th floor of Block B. In QC lab?
QC lab, no sir, we haven't yet. I mean, I have not yet worked in QC lab, so I haven't seen much.
Okay. Are there any other older students here? Lohit, I know. There are no other old students, like existing students of IT Hyderabad? Okay. Okay, fine. So in industrial structures, often rods are used. So if you have a rod and maybe you have a nut here at the end and some portion of the rod will be threaded, so then you take the root area of the thread. So if I can zoom in, the threads rather will look like this. Threads are usually cut into the original rod shape, right? So basically, this was the original thickness or original diameter of the rod. The threads are cut into the rod. Okay, so basically the root area will be the root area's cross section from here to here. This will be the net area available to you in a threaded rod. Okay, that's how you calculate the threaded rod area. So then there is a quick example. Let me take you to that example. So here there is a plate of 12-inch diameter thickness, width, sorry. The width of the plate is 12 inch. The thickness of the plate is 1/4 of an inch. The units here are inches, but that should not disturb you too much. The calculation is pretty much the same. The formulae are not unit dependent. And then there are these 4 holes A, B, C, D given on this plate. It is subjected to uniform tension. Tension force is acting around the centroid, so it is uniform tension. The locations of these holes are given. So the first hole is at 2.5 inches away from the edge. The second one is also 2.5 inches away from the first one. The third and fourth, they are both 4 inches away from the second one. Okay. And they are aligned in this direction. Then you have the other edge at 3 inches. The diameter of each hole is 15/16 of an inch. Okay. So 1/16 of an inch less than 1 inch. That is the diameter of a hole. Okay. So now you can consider several paths. One possible path could be this one, AD, correct? That seems like a shorter path. Alternatively, you may have ABC path of fracture. Okay. Or one may have ABD path. Okay, these are the only 3 possible paths which have any likelihood of governing. Okay. The difference between the ABC and ABD path are that the distance BD, that is 2 and 1/8 of an inch, and distance between 2C in this direction is less than that. So ABC probably will be preferable over ABD. We will see that. Okay, and then there is AD, of course, the direct path. So all you have to do is you have to calculate the net area considering the total path AD, the path ABC, and path ABD. So for path AD, what's the time by the way? For the path AD, we take the 12-inch thickness minus, there are 2 holes involved in this case. So 2 multiplied by the 2 holes diameter, 15/16. And the third hole is not involved. So there is, and there is no addition because of the inclined path. So the path is perfectly perpendicular. The entire path is perpendicular to the load. So there is no addition because of that. Okay. The total net section will be 12 minus 2 times the 15/16 of an inch. That multiplied by the thickness. So that is 2.53 inches square. That is the total net cross section for AD path. Similarly, net cross section for ABC path will be again 12. Now in ABC path, we have 3 holes that you have to pass through. So 12 minus 3 times the hole diameter Plus, now we have to see how many portions are inclined this time. So this time you can see here there are two portions that are inclined. Okay, so you have to take that s square by 4g component. Sorry, p square by 4g. You can also call it s square by 4g. P square by 4g component. So you have to do p square by 4g for this inclined path, and then p square by 4g for this inclined path. P square, that is 17/18. 17/8 is only this part, right? 2 and 1/8 of an inch. So that is basically, in other words, 17/8 divided by 4g. So this is 2.5 and 4 plus p square by 4g for this part. So this p is basically 1/7/8 of an inch. What is the meaning of p versus g? Which one is p and which one is g? How do we know that this is p, this direction is p, and this is g?
Depends upon the load. I mean,
So the interspacing between the
direction.
the direction.
In the direction of the load. Exactly.
In which direction load is applied based on that?
Yeah, so that is P. Very good. So P is in the direction of the load. So 15/8 is the P. So P square divided by 4 multiplied by G is also 4. And you can notice that P and G both are counted from center of the hole to the center of the hole. Okay, so that's what you use, and then multiplied by the thickness, and you get 2.46 inches square, which is smaller than AD. So ABC is smaller than AD. ABC is going to govern. Then path ABD, as we had discussed in the beginning, this, see, up to here, from here to here and up to here, the two are same, ABC and ABD. Where they differ is whether one goes here and the other one goes here. And the distance between B to C in this side is smaller than the distance between B to D. So obviously, the BD will be not governing because the area is longer in this case. And that's how it turns out to be. You can see that. So this time we do 17/8 of an inch for 2.5. This is for part AB. And for BD, you use this one, P square by 4G. And this one is larger, and therefore your net area turns out to be larger. So as a result, your net area is governed by ABC, 2.46 inches square. Okay, and if you have to calculate the capacity, and Fe415 is used, so for this steel, the Fy value of 36 KSI and Fu value of 60 KSI is given. 36 KSI, you understand what KSI is?
Kips per kilopound per square inch.
Yeah, kips per square inches. Okay, PSI will be pounds. Pounds is represented as lb per square inches. Okay, these are the units of stresses or pressure. So limit state of yielding for the gross cross-section area. So gross cross-section area is 12 into 0.25, that is quarter of an inch thick plate, divided by gamma m0 multiplied by Fy, and you get 98 kilonewton kips. Limit state of rupture, kips is basically kilopounds. Limit state of rupture, that is, again, we have 0.9 Fu An gamma m1. 0.9 Fu is 60 for that steel. An was 2.46, we had just calculated 1.25. This is gamma m1. The value is 106 kips. So the limit state of yielding of the gross cross section is governing. Okay. Now, two things I have not explained in this discussion. One is where is this 0.9 coming from, and why are these two 1.11 and 1.25 different? This we had discussed last time briefly. 1.11 versus 1.25. Why are these two different? Can anybody try to explain why are the two values 1.1 and 1.25? Different values are used for the two limit states.
Because, sir, for yielding, sir, if at all the material yields, there is much, strain hardening portion is also there. I mean, complete failure will not be there. But when in terms of net area of rupture, so it will become, although it's going under yielding, then again it's ultimately it will be collapsed then and there. So that's why they are taking higher material factor of safety there. Maybe this may be the reason. I don't know.
Okay, yeah. So actually, the real reason why they use two different factors is really this. That and also this 0.9. Can anybody suggest why this extra 0.9 is there?
The 10% is saved for dynamic.
What dynamic?
This 90% is saved for the static behavior, and
No, elaborate more. Sorry.
so the 90% strength is reserved for like static behavior, and the 10% is saved for the dynamic behavior, like that something.
I don't know. It's all designed for the static only. See whether what dynamics are you talking about? First of all, I don't know. I mean, are you talking about high strain rates? Because we are talking about resistance here. We are not talking about loads. So whatever dynamic effects you have to do when you did the analysis, those dynamic effects should have come into picture already. So actually, what happens is that, and this is relatively complex and things to understand, because not because technically it's complex. Technically it's pretty straightforward, but the way codes are developed. See, what happens here is that now for steel, what is the purpose of in the resistance factor? What is the purpose of using two different resistance factors, yield versus rupture? What was the purpose? The purpose was a particular resistance factor was meant to govern how unpredictable that value is. Okay, so let's say if you have more scatter on that particular value, then you use a higher higher resistance factor. So for example, if a material has a more scatter in the limit state of rupture, that is at what stress it ruptures, if there is more scatter there, then you would use a higher a higher value of factor of safety. You follow that? If there is more uncertainty, higher factor of safety. If there is a less uncertainty, that is more, you have more confidence in the test result, then you use less factor of safety. So what happens is that when you test a coupon and you get the value of yield value, that is your 36 KSI or 250 MPa, and you test a coupon and you get ultimate stress of 60 KSI or 415 MPa. In either case, the actual variation is not very significant. So the scatter that you get in the yield stress is also quite a little bit there, and also the scatter that you get in the ultimate stress is also there. Okay, and they are comparable. They are not significantly different. What happens is that when you have a plate like this, okay, and let's say you have some imperfections or something for whatever reasons, like these holes are not perfectly drilled and so on, and then the actual rupture strength of the plate, if you see, it has much more scatter, or predicting the rupture strength of the plate is much harder. You understand? So geometry also plays a role. It is not only the yielding of the coupon, because coupon is cut very nicely with smooth edges and everything. Okay. But when you actually have a plate and when you try to test it for yielding and when you try to test it for rupture, you will see that yielding, even if it happens at one place first, the next it will stain hardness slightly, and then other places will start yielding or it will start spreading. So overall, when the plate, you can say that the entire plate has, or entire length or cross section has yielded, that will be very easily quantifiable. Okay, but when you talk about rupture, you make identical 6 plates, you keep the entire fabrication process identical, but just make 6 different people do it, or get it done from 6 different fabricators, okay, and test them. You will see that they will give a very similar yield strength, but very different rupture strengths. Okay, you follow that? Because rupture is governed by the presence of micro cracks, presence of whether there are any imperfections, and so many other factors. Okay, which is not the case in the coupon. But for plates, for real life members, that is a reality. And because of that higher level of uncertainty in rupture behavior, we have a higher factor of safety for rupture. Then comes the question of 0.9. Why do we have 0.9? And that is where what Lohit was saying gives the answer. So basically what happens is that even if the member yields, it still has the reserved capacity of what? The reserved capacity of strain hardening available. So after yielding, it can still resist some more load, and it is not completely breaking apart. It's not completely falling apart. It's only become non-usable, significantly damaged, but it is not collapsing immediately. However, if once the rupture point is reached, the catastrophic effect it may have is that the entire building may come down immediately, entire structure may fall down immediately, because the two parts will separate as soon as rupture happens. Okay, so if one surface ruptures, the two parts that were connected together through that surface will completely separate, and that can bring down the entire structure. So that's why you want to add another factor of safety to account for the consequences, the catastrophic consequences that rupture can cause, that yielding does not cause. Okay, I hope that answers the questions. So that's how you have these two limit states: limit state of yielding, cross section yielding, or limit state of rupture for the net cross section. And how much time do we have? We have another almost 10 minutes. Okay, so net section rupture seems very nice, easily understandable. Now what happens is that, as I was mentioning before, not all members will always be subjected to uniform forces. So in this particular case, you can see that stresses are almost uniform, like it is acting right at the center. So you can assume that stresses are uniform. Okay, and then it works perfectly fine, this formula. But there are challenges to this formula. One challenge is limitations of this formula. So one possibility can be let's say I have this pattern of holes, and it may be my geometry requirements that the holes are aligned like this. Okay. Yeah, this is much better. Okay. So now, and this is the direction of the load. Now, in this case, what would be the load, the rupture path that I would consider that is most likely to govern? Can I say that comfortably that this will be the load, the rupture path? The alternate rupture path could be this one or this one, right? The alternate could be this, and one alternate could be this. But the most likely that most of you would understand will be this. Correct? Now, if that is the case, what is the p-value for this segment? P-value is given, easy. This is the length. What is the g value for this segment?
Same P.
Sorry? G is in the direction of load, right? Sorry, G is in the direction perpendicular to the load. So how far? So between this hole and this hole, G is whatever it is, and P is 0. Correct? Because P is in the direction of the load. But between this hole and this hole, my P is this distance, but G is 0. So my P square by 4G for this segment will be how much? Okay? You agree?
Yes, sir.
For this segment. So that means I cannot use that formula of P square by 4G for such kind of segments. Segments that are segments parallel to the load. Fine. it cannot be used. Then in such cases, obviously we know that when the T is acting and this kind of a rupture is possible, this surface, imagine when it separates, when it separates, it will be separating like this. Okay, correct? That means this surface will be in what kind of stress?
Shear.
Shear stress. Right? This will be in tension. This will be in tension. But this one will be in shear. So under shear, pure shear, this formula doesn't work. So that's where the requirement of block shear failure comes. There you consider the possibility of pure shear along with tension. Okay, that is one limitation of this formula. The other limitation of this formula is it does not work as beautifully when you have non-uniform stresses. You have a plate, but my stresses are non-uniform. For whatever reason. Okay. Then I cannot say, because then the stresses will be non-uniform, I cannot say that my net area is this much, as is given by this formula. So in such cases, so first we will take a look at the second limitation, that is your non-uniform stress distribution. And that is also known as, in this particular way, it is known as shear lag effect. When do we have shear lag? So you have an angle, like shown here, you can see the angle, and it is connected through a gusset plate, let's say, with these 4 bolts, and which is very common. So these 4 bolts are all on the same leg. Why don't you have the other leg connected? Why is it very common to connect only one leg of the angle? Why don't we connect both legs of the angle to the connected element, whatever?
So as to not to reduce the area of unnecessary stress constant.
No. So instead of 4, we could have done 2 here and 2 here, no?
Maybe the load is applied at the leg part only.
Yeah, but that is because only one leg is connected. If you had connected both legs, then the load would be applied at both legs.
I don't know.
Then we have to use another angle, sir.
Another angle.
Yes, sir.
To
connect to the gusset plate again.
To the gusset plate, yeah. So yeah, so like the design of the gusset plate becomes very complicated. Right now, you just have a plate. So for example, in order to get this design to work, that what you could see in that picture, all you have to have is you have this angle. I'm drawing it in 2D. So one leg is connected and one leg is, so this leg is connected basically with 4 holes. And this leg is not connected, it is outstanding leg. And all you have to have is a plate like this, which might be welded with some other member somewhere. Okay, so this gusset plate is welded with something else very nicely, straight plane surface you get. And to that gusset plate, you have connected this angle. And you calculated how much resistance one bolt offers, you multiply, you needed 4 times that much of force, you put 4 bolts. And then your requirement is satisfied. Okay, but now the challenge is that only one leg is connected, and as a consequence, the stress distribution in the leg, in that angle, is of this kind. This leg almost has a uniform stress, but the other outstanding leg is not under uniform stress. So the entire member is not going to fail simultaneously. So the strength, effective strength that is available to you will be reduced. Okay. So that is a very common situation. Now imagine that you had this angle as is shown here, this particular angle. And if I wanted to connect this leg also to this member, so this was the member, basically the purpose of the gusset plate is to connect 2 members together, right? So the purpose of this gusset plate was to connect member 1 with member 2. Now, this gusset plate worked fine, but it was connecting only with one leg of this member 2. But if I were to connect the other leg, this is this leg also, with this member, the member 1, how would I do that? That will make it very complex joint. So I have to put another plate which is inclined at another angle, or maybe I have to bend the gusset plate, which itself is a major issue. And then the member length is also not available in that direction. So that connection becomes very complex and not very commonly used. Okay, and with this is a very easily doable connection detail where you just connect one leg of the two legs of the angle. There are two legs in that angle, only one leg is connected, and that's how you distribute the forces. That is much easier to make. If I had a plate, then this would not have any. Instead of an angle, if I had just a plate, this was one member. I'm not going into the detail of what shape that member has. Then you had a gusset plate, and I had a simple plate to connect. Right. So then I would have simply put whatever number of bolts were required in that plate right at the center, and the stresses would have been uniform or could have been assumed to be uniform. But when I have an angle, then that thing hurts me. Okay. So then there are special provisions given, because this is such a common problem, that special provisions have been given for angles that are connected with single leg, and what is the tension capacity of such angles. Similarly, when compression members come, again provisions are given for angles that are connected with a single leg in compression. Okay, so there are old provisions and there are new provisions. Now old provisions have been turned into kind of a estimation kind of provision, so that you can use for estimation and proportioning of the member size, and then you should come to this clause to calculate the actual strength. Okay, so there is this factor called alpha. I think we are out of time, so I think I'll stop here today. In the next class, I'll talk about this particular clause of shear lag effect. Okay, I hope at least shear lag effect is clear to everyone, right? So I won't have to repeat what is shear lag. What is happening here is that force is getting transferred here. Therefore, this part, a portion of the cross section, is not resisting, and that is shear lag. Okay. All right, class. So I'll upload one more assignment, quiz, whatever you want to call it, today, and I hope you have submitted the one that was due today already. Fine. Okay, so I'm discontinuing the